announcements I would like to make before we move ahead. The first announcement is that on Friday we're going to have a problem solving session. So be there on Friday, and I will take it myself, and in the remainder of the course I will try my utmost that all the Fridays are dedicated to problem solving, and I'll try to take most of them myself. One. Number two, we give you homeworks and we provide you with solutions of the homeworks. Whether you hand in homeworks or not, that's your choice, but solutions are provided for you to read. So go through the solutions. And what I'm going to do now is that when I taught this course in 2009, all the homeworks, all the quizzes, all the exams and their solutions, I'm going to put up a zip file or a consolidated PDF on the website as well, so that there's sufficient practice for you, so that you can look at those questions and look at those solutions. Third thing, modern physics or any physics cannot be read with a highlighter, a yellow highlighter and an orange highlighter, and you just highlight what you read and think that everything is absorbing into your bloodstreams and it's perfusing to your brains and it will live with you forever. You have to practice. Physics and mathematics, they have to be practiced, and you have to write what you read. So without practice and without being able to solve questions, without practicing, you will not be able to do well in this course, and you will not be able to understand what I'm trying to teach. I'm trying my best to teach you. Of course there will be deficiencies, but unless you reciprocate and you work harder than I do, there won't be much point in attending this class. So please practice. There is no substitute to practice. We've seen your midterms. I think you could have done much better. Seen your homeworks. The level of interest is not what I expect or what I expect it to be. So please take interest in the course. On Friday I will also prepare a small presentation about 10-15 minutes of where modern physics is used in biology, chemistry, electrical engineering, because you shouldn't think that this is all a figment in our imagination, a figment in our mind that does not have any real practical applications. Quantum mechanics permeates our lives. It permeates technology. 75% of the devices that electrical engineers make and use in today's computers, 75% of all the revenue that comes in microelectronics and nanoelectronics comes from devices which are built upon quantum mechanical principles. You cannot live without quantum mechanics. From your genetic makeup, your genotype, all the way to photosynthesis, all the way to how diodes work, how transistors work, how computers work, radioactivity, which you always use in hospitals for radiology and for therapeutic treatment, lasers, the universe as a whole, it's all coming from quantum mechanics. So it's not a useless subject. And this new term that I'm often hearing from students, that we are force enrolled into this course. You're forced enrolled because we as educators and teachers believe that every engineer, every scientist of the modern time needs to study a little bit of quantum mechanics. And when you go out into the field, unless you're doing a management job or if you're doing science and engineering in your careers, you'll remember that there was such a thing as quantum mechanics, and it is really useful. And this is what will give you the edge from engineers who come out from UET, engineers who come out from NUST, engineers who come out from NED. This is the edge that you have. So I would like to keep on building the case that modern physics is important for you. Alright, so we will continue our discussion of the hydrogen atom, and no more homeworks. This is the last homework that I gave you. I think homeworks are not serving the purpose. I'm going to replace the homeworks with quizzes. No more homeworks. And what I'm going to do is I'm going to upload all the material from the course I taught in 2009 with the solutions, so that you can practice as much as you can. You have 2 books available with you. Look at the end of the chapter problems. Try to solve those problems. Of course you can't solve all of them. Some of them are really difficult. But at least try. That is how you will, unless you apply your knowledge, you will not be able to understand it. In 3 hours of lecturing per week or 2.5 hours of lecturing per week, I cannot cover everything. I'm just scratching the surface of the landscape. Because now you're grown-ups. I'm just hinting you in the right direction, and you have to move in that direction on your own. You're university students now. All right. So we've looked at the angular part of the Schrodinger equation and the solutions, and we now have a fair idea of what orbitals look like and why do they look like the way they're normally drawn in chemistry books. There is a third part of the wave function that we have missed so far, which is the radial part. So today we're going to look at the radial part, and we're going to close the picture of the hydrogen atom. We're going to see in a capsule form of what the hydrogen atom really is. What was the Bohr's model, which is generally called the old quantum theory, and what's the picture that is emerging from the Schrodinger picture, which is called the new quantum theory. So Bohr's model is really an old quantum theory, and the Schrodinger picture gives us the rudiments of a new quantum theory. And at the end of this lecture, I will ask you what's the difference between the old and the new theories. Because we've actually seen the difference in all of these lectures that I've given. So the wave function, which is defined by 3 quantum numbers n, l and m, and depends upon 3 variables r, theta and phi, must be a product of a radial part, a polar part, and an azimuthal part. And this part was called a spherical harmonic function, and it depends upon L and ML and the variables theta and phi. So theta is dependent on L, ML, phi depends on ML. So we can solve the Schrodinger equation for the radial part, and the solution is complicated. Interested readers can look it up, but the solution takes a general form, and this R depends on the quantum numbers n and l. We notice that phi depends upon ml, theta depends upon l and ml, r depends upon n and l. अभी हमने ये देखना है कि what is the physical meaning of n, l and ml. So r, which is a function of small r and is dependent on n and l, is given by exponent minus z, which is the atomic number, n over a naught zr over a naught raised to power l, and some polynomial g and l zr over a naught. So we have exponent of r, negative r, so it's a decaying exponent. As r goes up, this factor drops. We have an r raised to the power l, so as l goes up, this factor goes up, but it doesn't go up exponentially, it goes up polynomially, and we have some polynomial of r. And if you notice, r is always appearing in combination with a naught. R over a naught here, r over a naught here, r over a naught here. And a naught is, what is a naught? Is the Bohr's radius. 4 pi epsilon naught h bar squared over me squared, and is almost 0.529 angstroms. You don't have to remember this formula, but you can easily find it, and if I would give this formula to you in the exam or in quizzes, so this polynomial would change with the value of n and l. For example, for n equals 1, L must equal 0. So this is the 1s orbital. The radial function is simply proportional to exponent minus z r over a naught. N is 1. This thing is 1 because L is 0, and this polynomial is also 1. And we also notice that in the n equals 1, L equals 0 state, what about theta and phi? Do they have any dependence on theta or phi? In the s orbital, do we have any dependence on theta or phi? No, we don't. So at the most, theta and phi can be, they are proportional to a constant, they are equal to a constant, they do not have any theta or phi dependence. So the wave function is just the radial part, it does not have any theta or phi dependence if n equals 1 and L equals 0. So if you look at this radial part of the wave function, the total wave function for n equals 1, L equals 0, ML must also be 0 as a result, r theta phi is proportional to some constant, is equal to some constant times the radial part, exponent minus r over a naught. I take just the hydrogen atom, so Z equals 1, the atomic number is 1. So this is the wave function for an orbital. Which orbital are we talking about here? This is the 1s orbital. So this is the wave function for the 1s orbital. Now could you, it's a real number. जी ये n और l पर डिपेंड करता है. When n is 1, L is 0, this polynomial is 1. ठीक है? So this comes out from solving the Schrodinger equation. This polynomial will change with n and l. For n1, L0, this polynomial is 1. I will always provide you with what this polynomial is. Now can you plot the wave function and its modulus squared? Please plot the wave function and the probability density for the 1s orbital. Now please don't plot in polar coordinates. In polar coordinates we know that we have a sphere for the 1s orbital. Now what I would like you to draw is the wave function as a function of r, that is psi 1 0 0 and psi 1 0 0 mod squared. I would like you to plot these quantities as a function of r, because there is no theta or phi dependence. आर नेगेटिव तो नहीं हो सकता.
फंक्शन रियल है वो बस स्क्वायर हो जाएगा ये स्क्वायर
So this is just a decaying exponential, goes down like this, and this is also a decaying exponential, but the square of a square of a decaying exponential, but it decays faster because it's a square. Now let's look at the 1s orbital closely. We know that the 1s orbital is spherically symmetric. Can you plot the 1s orbital as an electron cloud, keeping in mind your polar diagram and your radial probability density? पहले हमने s orbital को प्लॉट किया था. This is y axis, z axis, and the s orbital was drawn like a sphere because there is no theta dependence or phi dependence. आप जो बच्चे पीछे बैठे हुए अगर आप नहीं पढ़ना चाह रहे तो आप चले जाएं बेशक. तो जब हमने s orbital को प्लॉट किया था, we just draw a circle or a sphere because there was no theta dependence or phi dependence. We had total spherical symmetry. But we were not concerned about the radial part of the wave function or the probability density as we go away from the nucleus. Now this is the radial part. We have to combine the radial part and the polar part. And the best way to draw this is to make a scatter of points. Where will the points be? Will they be densest? They will be densest at the nucleus. So we will have a very dense population of points at the nucleus. That is, if we were to find the electron, intuitively or mathematically we see that the electron has maximum probability of being located at the nucleus. This seems counterintuitive because we know from the uncertainty principle the electron cannot exist inside the nucleus, so we cannot confine the electron to a very small region such as the nucleus because then its energy is so high that the electron will fly away. So this violates the uncertainty principle. But at least this is what is appearing to come out from the mathematics. But if we plot a scatter plot, we have a very high density of points at the nucleus, and this density gradually diminishes. At any one radius, the density remains the same because of the spherical symmetry. That is, you go along a circle, the probability density does not change. The modulus squared of the wave function does not change. You draw a circle here. On this circle, the probability density remains the same. On this circle, the probability density remains the same. On this circle, the probability density remains the same because there is no theta and phi dependence. The spherical harmonic function corresponding to these quantum numbers is just 1, is just a constant. However, if you move away from the nucleus, there is a gradually decreasing probability density. So this is what an s orbital really is. That is the highest value of the modulus squared of the wave function at the nucleus, and this probability density decreases and it goes to 0 further away from the nucleus because as r goes to infinity, the probability density goes to 0. But here we have a fix. We face a problem. The problem is that, so it appears, according to this calculation, the electron has maximum probability of being located at the nucleus.
सर हम उसपे क्यों मिली है न्यूक्लियस पे मैक्सिमम प्रोबेबिलिटी डेंसिटी क्यों मिली है?
देखो रेडियल प्रोबेबिलिटी डेंसिटी अगर आप देखें इसको फंक्शन को प्लॉट करें, इस फंक्शन को जब आप प्लॉट करते हैं तो r0 पर इसकी मैक्सिमम वैल्यू है, ठीक है. तो दिस इज अ सॉल्यूशन ऑफ द श्रोडिंगर इक्वेशन.
वही मैं कह रहा हूँ इसके हमें कैसे पता ये हम ऑलरेडी
ये सॉल्व करता है श्रोडिंगर इक्वेशन को. दिस इज द ग्राउंड स्टेट ऑफ द हाइड्रोजन एटम. इट सॉल्व्स एग्जैक्टली द श्रोडिंगर इक्वेशन. नाउ वी हैव टू सॉल्व द प्रॉब्लम दैट वी आर फेसिंग हियर. The electron has maximum probability apparently of being located at the nucleus, but we know from our previous discussions that the electron does not exist at the nucleus. Otherwise the atom cannot be stable. If the electron always falls into the nucleus, no atom will be stable. We are matter and we will all pop out as energy and disappear and be annihilated. We cannot exist if this were the case. ठीक है, तो atoms को stable होना है, अपनी जिंदगी को रवान दवान रखने के लिए एटम को स्टेबल होना जरूरी है. सो दिस इज एन इम्पॉसिबिलिटी. सो हाउ डू वी एक्सप्लेन दिस अपैरेंट पैराडॉक्स? ठीक है, इसको एक्सप्लेन करना है. अच्छा, उसको एक्सप्लेन करने का एक तरीका है और वो तरीका ये है कि सपोज I ask you the question, you are in three-dimensional space. What is the probability of finding an electron in a small volume centered at r theta phi? In three dimensions I make a small volume whose coordinates are r, theta and phi, and I want to find the probability of locating the electron in this small volume. So what will this probability be? What will this be equal to? What is psi mod square? That's the probability density. So you multiply the probability density with the small volume. Suppose this is a very small volume. Can you write the expression that I should write on the right hand side?
वॉल्यूम इतना स्मॉल होगा, इसकी वजह से प्रोबेबिलिटी जीरो हो जाएगी वहाँ पे
न्यूक्लियस पे.
और न्यू ग्राफ आएगा.
हाँ, करके देखो जरा. बिल्कुल ठीक है. अब dv को लिखो. dv क्या होगा? पोलर कोऑर्डिनेट्स. चावल dv dv
नंबर आएंगे.
ठीक है. अब dv को लिखो.
ये dv वही होगा जो हमने पहले, फिर उसका बाद मॉडुलस को dv में इंटीग्रेट भी करेंगे.
अभी इंटीग्रेट नहीं करना. So we will just have modulus of psi square into dv, small volume, and the volume is centered at r theta phi. So we will have dv is replaced by r square sine square theta dr d theta d phi. Now this comprises a radial part, a polar part and an azimuthal part. So I can actually write r squared or r modulus squared capital theta squared capital phi modulus squared r squared sin theta dr d theta d phi. ये साइन स्क्वायर थीटा क्यों आया? साइन थीटा, आई एम सॉरी. ठीक है? So this is the volume element that we've derived in one of the lectures. So now if we this is the radial part, it only depends on radius, this only depends on theta, this only depends on small phi. So I can separate out the radial part. So I can write small r squared capital R squared. I can write this separately. Sin theta, I can write this separately, and I can also write this separately, dr d theta d phi. So this is the probability of locating the electron in a small volume. Let me draw the Cartesian axis x, y and z. The question that I now pose is, what is the probability of finding the electron between r naught and r naught plus dr? But this is a question that I pose to you. That is, on this three-dimensional space, I draw what is called a shell. एक शेल बनाता हूं जो अंदर से हॉलो है, लेकिन उस शेल की कोई थिकनेस है. So this is my shell. And the inner radius of the shell is r naught, and the thickness of this shell is very small, it's dr. Now the electron is in a certain orbital given by a combination of n, l and ml. It has a certain wave function, and the question I pose to you is, what is the probability of finding the electron in this shell? Now can you write the answer to this question? Make an integral or write something that gives me the result, that gives me the answer to this question. जीरो से कहाँ तक? थीटा को कहाँ से कहाँ तक करेंगे? जीरो से ये अंदर वाला होगा, उसको जीरो से 5 टाइम्स कुछ से नहीं, थीटा को जीरो से पाई तक करेंगे ना. फाई को जीरो से 2 पाई और थीटा को जीरो से पाई.
for the electron in the r0 से r0 plus dr को 0 से 2 pi और 0 से pi theta और phi.
So pi would be minus 5 to pi?
5 या 0 से 2 पाई कर लो, माइनस पाई से पाई कर लो, एक ही बात है. Alright, you already have a fair idea of what I'm trying to ask. और इसका आंसर ये होगा कि r square dr, since this part is radial, purely polar, purely azimuthal, I can write this as a product of three integrals. R goes from r0 to r0 plus dr. I can even make a further simplification, I'll tell you in a minute. The polar part can be integrated separately because it only depends upon theta, sine theta, d theta, और थीटा की लिमिट्स होंगी फ्रॉम 0 to pi मल्टीप्लाइड बाय d phi from 0 to 2 pi. So this is really the probability of locating the electron in this small shell. इनका क्वेश्चन है कि आप इंटेग्रल्स को इस तरह सेपरेट कर सकते हैं. इफ यू हैव एन इंटेग्रल लाइक दिस x y dx dy and x and y are totally independent. If x and y are totally independent, that is y is not a function of x, then you can write this as x dx y dy. Because when you're integrating with respect to x, y is just a constant, it comes out of the integral. So if x and y are independent, you can write this as a product of integrals. That's what I've done here. R, theta and phi, all three of them are independent. If dr is very small, if dr is extremely small, I can replace the first integral. The first integral simply becomes r squared, capital R squared dr. Right. ठीक है, ये एक छोटे सा एक पॉइंट है. अब स्टूडेंट ने सवाल पूछा कि हमने dv की जगह 4/3 पाई r क्यूब क्यों नहीं रखा. 4/3 पाई r क्यूब तो पूरे क्यूब का वॉल्यूम है ना. हाँ, अब ये आगे सिंप्लीफाई हो जाएगा, वो मैं अभी बताता हूँ कि ये चीज सारी 4 पाई के बराबर आएगी. So this is really the probability of finding the electron in this thin shell. Now if you observe, there is an r square factor here. There is an r square factor here. If you want to find the probability of locating the electron in another shell which is further away from the nucleus, you get a bigger shell. Now this volume is bigger, but the probability density for the s orbital is decreasing exponentially. So this volume is bigger, but the probability density is decreasing, because as you're going further and further away from the nucleus, the modulus squared is decreasing. So the modulus squared, that is the density of points, is decreasing as you're going further away from the nucleus, and the thickness or the volume of this shell, or the volume of this shell is also increasing, because now you have a bigger shell. you go further away, you have even a bigger shell. But the probability density is decaying exponentially, it's decaying very fast. So as a whole, this term is decreasing because this thing is decreasing rapidly as small r is increasing. This is exponential, even though r square is going up. So there is a balance that has to be played. That is, the probability density is decreasing as we're going away from the nucleus, and the volume of the shell is increasing. So we really have to multiply r square with the probability density, with the radial probability density squared. If you come closer to the nucleus, what is happening is that the probability density is increasing because the probability density is maximum close to the nucleus. The probability density is going up, but the volume of this shell is rapidly diminishing. It's diminishing. It's going down. You move further towards the nucleus, the volume of this shell has shrunk further. And the probability density has gone up, but the volume of the shell has gone down. At the nucleus, you just have a point, which means that at the nucleus, r is 0. Small r is 0. Even though this is the largest. But this is not infinite, remember. This is not infinite because your wave function has to be normalized. ठीक है, ये infinite तो नहीं हो सकता, ये a की value infinite तो नहीं हो सकती ना, ये कोई finite number है. तो at the nucleus, even though you have maximum probability density, which means you have maximum modulus squared of the wave function, but your radius is so small that this infinitesimal volume approaches 0. So what we really have to look at is not r mod squared, but we have to look at the product of r square and r mod squared. And we define what is called a radial probability density. I denote it by P small r, and the radial probability density is defined as the probability of finding an electron at a radius r. That's the probability of finding an electron at a radius r. The probability per unit length. ठीक है? And this PR is given by r squared and the modulus squared of the radial part. This is just this factor PR, the radial probability density. I will write a small r as well to show that this is radial, and it depends upon the radius. So P sub r means the radial probability density. So if one asks you the question, what is the probability of finding the electron at a radius r? We cannot simply use r modulus squared. We have to use r squared, small r squared, multiplied by the modulus squared of the radial part. Okay? So now if we look at the modulus squared of the radial part, which is given by this decaying exponential, and on another graph, if we plot this r squared, so we plot r squared here, we get a parabolic curve. Now when we multiply this modulus squared of the radial part with r square, what do we get? Can you try plotting the product of this decaying exponential with this parabolically increasing radius squared? What do you get? Plot karo zara. Gaussian?
Yes, Gaussian.
गॉसियन तो नहीं होगा, गॉसियन से मिलता जुलता होगा, लेकिन सिमेट्रिक नहीं होगा, सिमेट्रिक नहीं होगा।
जिस तरह तो इनिशियली हीप बनी होनी और फिर डिक्रीजिंग।
बिल्कुल, ये केमिस्ट्री में पढ़ा हुआ है।
यस सर,
केमिस्ट्री में पढ़ा हुआ है।
सर अभी प्लॉट खींचने का गलत बना हुआ है।
पढ़ा हुआ रेडियल प्रोबेबिलिटी डेंसिटी। So if I plot the radial probability density, I start off from 0. I always start off from 0. And this is what my function looks like. So if someone asks you the question, what is the probability of locating the electron at the nucleus? It's 0. Because the correct concept to use is not just the probability density, but the radial probability density. So as r goes up, the radial probability density increases, and then the radial probability density decreases, because this is a decaying exponential. In this region between negative and the maximum, the effect of the increasing r square is winning. But beyond a certain stage, the exponent has decayed so fast that the decay effect dominates, and this is not symmetric. So in MATLAB you can plot this function and plot this function and do a point by point multiplication of these functions and achieve this curve. And something that I will tell you at the outset, which you probably already know, is that the maximum of this radial probability density is the Bohr's radius. This is something you already know. And can you find this maximum? आपने किया हुआ ये? केमिस्ट्री में पढ़ा हुआ ये? ग्राफ पढ़ा था। तो अब आप इस तरह करना कि ये रेडियल पार्ट है, दिस इज द रेडियल पार्ट ऑफ एन s ऑर्बिटल, ठीक है? सो फॉर 1s the radial part is a exponent minus r over a naught. The modulus squared of the radial part is a squared exponent, आगे क्या लिखूं, minus 2r over a naught. The radial probability density p sub r function of r is a squared r squared exponent minus 2r over a naught. Okay, I want to find where this probability, radial probability density, is maximized. At what radius is this maximum? So I would simply differentiate this, equate it to 0, and find the maximum of this function. I will put this equal to 0. Equate it to 0. I will find the radius at which this function peaks, and it turns out to be exactly equal to a naught. Now the question is, which I would like to ask you, you have this result. A naught is the Bohr's radius. It comes out from the Bohr's model. The Schrodinger picture tells us a different story. But at a certain point, the Schrodinger picture and the Bohr's pictures meet. Now I would like to pose the question, what is the basic difference between the Bohr's model and the Schrodinger picture that we've just seen? One, and do the two pictures meet at some stage? एक मिनट दो, मुझे बताओ ना, खुद से सोचो, पहले मैं आपसे पूछूंगा. The first part of my question is, how are the Bohr and Schrodinger pictures of the hydrogen atom different? And how are they similar? Where do they converge? Do they converge at some point? आप क्लास में शुएब है ना? शुएब नहीं आए क्लास में? कौन है? शुएब हसन आज नहीं आया? चलो आप जवाब दो मेरी बात. अच्छा बोलो.
प्रॉब्लम में कहा था कि क्वांटाइज्ड ए नॉट पे ही इलेक्ट्रॉन फाइंड हो सकता है, जबकि श्रोडिंगर में की प्रोबेबिलिटी डेंसिटी है उसके अराउंड भी हो सकते हैं फाइंड.
ठीक है, कोई इसको इम्प्रूव करना चाहेगा इस आंसर को?
मैक्सिमम प्रोबेबिलिटी डेंसिटी ए नॉट पे होगी, ए नॉट टू ए नॉट मल्टीपल पे होगी, लेकिन जो उसके दरमियान भी एग्जिस्ट करती है, लेकिन बोहर्स के पॉइंट्स के मुताबिक सिर्फ ए नॉट या टू ए नॉट पे होगी दरमियान में, यानी कि वो कहीं भी इलेक्ट्रॉन एग्जिस्ट नहीं कर सकता.
ठीक है. बोहर ने कहा था, शाबाश, बोहर ने कहा था कि अगर ग्राउंड स्टेट में है तो द इलेक्ट्रॉन has to be at, it's in an orbit, this is the nucleus, the electron has to be in an orbit, in a circular orbit, which is always at a distance a naught, in the ground state. So the electron is destined to move at this radius a naught always. So he quantized the levels, that is, he said that the electron's level is quantized, it can only exist in this orbit. It cannot have a radius smaller than a naught or greater than a naught. तो उसने quantization introduce की, but the quantization was incomplete. The Schrodinger picture emerged, which tells us that there is a radial probability density. The electron, you can perform an experiment, even though the electron is in a 1s orbital, which is a ground state. The electron is in its ground state, the atom is in the ground state. You can perform an experiment in which the electron is detected somewhere closer to the nucleus as compared to a naught, or somewhere further away from the nucleus as compared to a naught, because the electron is now a wave. The electron is now a wave function. The electron is now a quantum field. It exists everywhere in space, where the radial probability is not zero. So it exists everywhere in space. This is the radial probability distribution for a single electron in the ground state. So you can detect the electron anywhere, but the maximum likelihood of finding the electron is at the Bohr's radius, and that is coming out quite naturally from the Schrodinger picture. Therefore, the Schrodinger's picture is the new quantum theory. It treats electrons as waves which are spread out in space as wave functions. We call them wave functions or quantum fields. And you collapse the field onto a point, and you perform the experiment on a large number of hydrogen atoms which are in the ground state. In most cases, that is the highest, if you make a histogram of where the electron is, the histogram will peak at a naught. That is what is the meaning of quantum mechanics. So the old quantum theory and the new quantum theory are different. They present different points of view, but the result converges at one point. That is, where is the maximum likelihood of locating the electron? If the electron is in the 1s orbital, it's at a naught. ठीक है? तो ये old और new quantum theories में फर्क है, but they converge at some point. Now if you look at the radial probability density and you want to find out the average location of the electron, where the electron is located on average. So I have this radial probability density, which is simply r squared, capital R squared. I want to locate where the electron is present on average. Can you write an integral? Don't solve the integral. Can you write the integral that gives me the answer? इंटेग्रल लिख सकते हो आप? क्वेश्चन नहीं समझ आया? आई वॉन्ट टू फाइंड द एवरेज रेडियस. किसे?
जो इंटेग्रल है उसमें आर की वैल्यू एक और एक्सपेक्टेड वैल्यू निकालने के लिए
शाबाश. All right. So the average value of R will simply be given by, because the wave function is psi mod squared, we have an R squared sin theta d theta d phi. This is the volume element, this thing. To find the average value of any variable, it could be radius, you just multiply this with R and integrate. ठीक है? So you integrate, theta goes from 0 to pi, phi goes from 0 to 2 pi, and R goes from 0 to infinity. So the average radius, this is the recipe to calculate the average radius. I can also ask the question, what is the probability of locating the electron at a distance a naught, and in between the angles theta, 0 and 90 degrees? देखो, ये एक सवाल मैं आपसे पूछता हूं. The radius of, at a radius a naught, an electron is in the, suppose in the 1s orbital. What is the probability of finding the electron such that theta is between 0 and 90 degrees? इसका आंसर मुझे आपने जुबानी बताना है. इलेक्ट्रॉन इज इन द 1s ऑर्बिटल. मैं जिससे पूछूं, आपने पुकारना नहीं, मैं जिससे पूछूं होता है. Anyone in the last two rows of the women sitting there, बता सकते हैं आप कि what's the probability of locating the electron in the northern hemisphere between 0 and 90 degrees? We're in the 1s orbital. आप इसका इंटेग्रल भी लिख सकते हैं, लेकिन ये तो जुबानी भी बता सकते हैं आप. Anyone? डरना नहीं, अगर गलत हो जाए जवाब तो कोई बात नहीं. आप तीनों में से कोई बता सकता है? इन्होंने जवाब दिया 1/4. 1/4 नहीं, 1/2, क्योंकि थीटा की टोटल वेरिएशन है फ्रॉम 0 to 180 डिग्रीज. ठीक है? So between 0 and 90 degrees, it's a spherically symmetric situation. You're in the 1s orbital. It's like a sphere. So there is 50% probability of locating the electron in the northern hemisphere, so to say. 50% probability of locating the electron in the southern hemisphere. I can choose any range of thetas, phis and r's. You just need to know what the general recipe of calculating the probability density is. Okay? Now always be sure of the normalization constants. In fact, explaining normalization constants will confuse you. So when we do problems on Friday, you will have a good hang of normalization constant, what the normalization constants in different cases are. But remember that if you don't have r here, you don't have this thing, this integral always goes to 1, because the probability of locating the electron somewhere is 0, anywhere or somewhere is 1. The electron must exist somewhere. Now I would, in the last 15 minutes, I would like to turn to the question of the physical meaning of the quantum numbers. We have 3 quantum numbers, n, l and ml. Schrodinger की theory हमें 3 quantum numbers देती है. Dirac, जो एक electrical engineer था, Paul Audrey Morris Dirac, एक electrical engineer था, उसने बताया कि there is a 4th quantum number which is called the spin. That is what we'll deal with next week. But in the Schrodinger's picture, there are 3 quantum numbers because we have a 3-dimensional system, n, l and ml. Now let's look at the meaning of these quantum numbers, physical meaning of these quantum numbers. The first of these numbers is n. Remember when we were dealing with the 3-dimensional well, we had 3 quantum numbers, nx, ny and nz. इन 3 quantum numbers की क्या significance थी 3-dimensional cubic well में? All 3 of them were quantizing the energy. The energy was quantized based upon nx square plus ny square plus nz square. Did nx have a separate significance of its own? Did nx on its own quantize something? देखिए, localization leads to quantization. So you're localizing the particle in the x dimension, it must quantize something. What is it quantizing? The momentum along the x direction. Because the wavelength is quantized, you have a standing wave. Therefore, this is quantizing px, this is quantizing py, this is quantizing pz. And energy is also quantized. Pi square, h bar squared, for a symmetric well 2ml squared plus nx squared plus ny squared plus nz squared. So localization leads to quantization. You're localizing the particle in 3 dimensions. So there are 3 variables, 3 physical variables, momenta, which are being quantized, and these are linear momentums. In the hydrogen atom we have a spherically symmetric situation, so we have to quantize something. So the 3 quantum numbers n, small l and ml in their own right quantize something. N quantizes the energy, E, and this is something that comes directly from the Bohr's model as well. The Schrodinger gives you the same result. The energies are quantized according to n, and the energies are given by minus me4 2 into 4 pi epsilon naught h bar squared capital Z squared, which is the atomic number squared. For hydrogen it's 1 over n squared. And this is, you all know, 13.6 electron volts. So in hydrogen, n quantizes the total energy. L quantizes something else. ml quantizes something else. Now L quantizes the orbital angular momentum. Now I can show that to you. It's let me show that to you. It will give you some motivation. I'm writing the radial part of the Schrodinger equation. Alright, so this is just the radial part of the Schrodinger wave equation. You don't need to remember this, I've written it for you. Okay? Now look at this equation carefully. On the right hand side there is an energy. Okay? There is an energy. On the left hand side there must be a quantity that equals the total energy. And energy we know has two parts. It has a potential energy part and a kinetic energy part. Where is the potential energy part? This is the potential energy part. So the rest must be the kinetic energy part. Okay? Now let's look at this expression. Now what we really have here, कोई नहीं सिर्फ 10 मिनट रह गए, कोई बात नहीं. Now what we really have here is that these two terms are kinetic energy. They represent kinetic energy. ठीक है? अब look at this term that I've written in the yellow box. If we have a system in which there is a center of mass or an axle and an object of mass small m of radius r is moving around the axle, it's rotating around the axle, it's revolving around the axle, okay? Like the earth revolving around the sun. This object will possess an angular momentum. Suppose the orbital angular momentum or the angular momentum is L. Okay? Now can you tell me what the kinetic energy associated with this angular momentum is, or what is the angular kinetic energy of this object? Mechanics का सवाल है. Half I half I omega square. This is the kinetic energy. Can you write this in terms of the angular momentum? जी
L square over m r square.
L square. ठीक है. L square square.
So L square over m r square into half L.
मैं भी कर रहा हूँ. ये नहीं होगा सर. नहीं ये डिवाइड करके.
ओमेगा को एलिमिनेट करो. L और I की टर्म्स में मोमेंट ऑफ इनर्शिया. L square over 2I. Do you agree with this? L squared over 2I. I is the moment of inertia. देखो, energy is momentum squared over 2 times the mass. P square over 2m is the energy. In the angular coordinates, L square over 2I. I is the moment of inertia. L square, and what is the moment of inertia here? mr squared. So if you look at this term and you identify that the denominators here are the same, this is 2mr squared, this is 2mr squared, and if this object, okay, if you look at this object, look at h bar. What are the dimensions of h bar? H bar की dimensions क्या हैं? डायमेंशंस, यूनिट्स नहीं, h बार की डायमेंशंस एनर्जी ओवर एंगुलर स्पीड which is just angular momentum. h बार की डायमेंशंस एंगुलर मोमेंटम की डायमेंशंस के बराबर हैं, ठीक है. So h bar has dimensions of angular momentum and this object, this is dimensionless. ये तो numbers है ना, L is just a number. So the numerator has dimensions of angular momentum squared. So this object is simply the angular kinetic energy and the numerator represents the modulus squared of the angular momentum. L squared equals L plus 1 h bar squared. So small l is quantizing the angular momentum. Because L is quantized. For a given n there are only allowed values of L. When small l is quantized, the angular momentum is quantized. So L is quantizing the angular momentum, capital L. So the electron, when it's moving inside the hydrogen atom, it has a certain orbital angular momentum, L. And that is quantized, and it's quantized according to the quantum number L, small l. ठीक है. और third quantum number quantizes something else, and it quantizes the z projection of the orbital angular momentum. Just two examples. देखो, स्मॉल एल क्वांटाइज कर रहा है एंगुलर मोमेंटम को, उसके मैग्नीट्यूड को. कैपिटल एल इज अ वेक्टर, एंगुलर मोमेंटम इज अ वेक्टर, एंड दिस इज जस्ट द मैग्नीट्यूड स्क्वेयर्ड ऑफ द वेक्टर. द मैग्नीट्यूड ऑफ द वेक्टर इज बीइंग क्वांटाइज्ड. Energy is a scalar, so it just has a magnitude, but the angular momentum has a direction and a magnitude. Small l is quantizing the magnitude of the angular momentum. Small ml is quantizing one of the components of the angular momentum. We call it the z component. मैं भी एक एग्जांपल दूंगा जिससे वाज़ेह होगी. एक एग्जांपल सिर्फ 3 मिनट में. अच्छा, इसको हम देखेंगे. लेकिन now we have n goes from 1, 2, 3 all the way up to infinity. L depends upon n and it can take up values from 0, 1 up to कहाँ तक जा सकती है इसकी values? n-1 तक. और ml takes up values 1, 2 up to L, -1, -2, -L. Now let's draw the structure of the hydrogen atom that emerges from this picture. We have one orbital. What is the ground state? The ground state is when n is 1, L must be 0, ml must be 0. So we draw a state here. N is 1, L is 0, ml is 0. So these are the values of n, L and ml. And it has a certain energy given by -13.6 electron volts, which is simply this number, because this is now 1. The next level, which is called the excited state, could corresponds to n equals 2. देखो next higher energy n equals 2 की होगी ना. अब when n equals 2, L can be 0 or 1, and with this combination ML is always 0, and with this combination ML can take 3 values, 1, 0, minus 1. So now what we really have is we have 4 wave functions. 4 wave functions. 4 combinations of N, L and ML. All 4 of them have the same energy. So we can draw it in different ways. This is 2, 0, 0, and these are 2, 1, 0, 2, 1, 1, 2, 1, minus 1. All 4 of these levels have the same energy, because all of them have n equals 2. So this is the n equals 2 stage of the hydrogen atom. This is the n equals 1 stage of the hydrogen atom, which means that the n equals 2 stage, 1 energy, 4 wave functions. लेकिन wave function तो सबके different होंगे ना, because they have different combinations of quantum numbers. We have 4 different wave functions. This is an s orbital, and these are p orbitals. Pz orbital, px orbital, py orbital, or the orbitals that we studied. There are 3 kinds of p orbitals, and there is 1 kind of s orbital. This is called a 2s orbital, and these 3 are 3 kinds of 2p orbitals. But all 4 of these orbitals have the same energy. So this is a 4-fold degenerate state. For the n equals 3 level, we can have a 3s orbital, we can have 3p orbitals, and we can have 5 3d orbitals. And all 9 of them have the same energy, because all 9 of them belong to the n equals 3 stage. Okay? So this is a 9-fold degenerate state. Corresponding to n, the degeneracy of the levels is n squared. If n equals 4, you have a 16-fold degenerate state. Now what happens in spectroscopy is that you make transitions between these levels. You can have a transition from 2p to 1s. You can have a transition from 3p to 1s. You can have a transition from 3s to 2p, from 3d to 2p, and so on. And each one of them will have a precise energy. The photons will have precise energies. It's not possible to make a transition easily from the 2s to the 1s level. It's not possible, because angular momentum is not conserved, but this is beyond the scope of this. So there are certain allowed transitions between these levels. And this is how you can find the spectrum of hydrogen, be it the emission spectrum or the absorption spectrum. So on Friday, we will start looking at a few problems, especially the problems associated with L square and Lz. One thing I would like to end this lecture with is, you have a hydrogen atom. Can you define a z-axis? You see, the hydrogen atom is totally spherically symmetric. There is no preferred z-axis. So what does the component of the angular momentum on the z-axis mean? When we talk about the pz orbital, it has maximum probability density along the z-axis, but where is the z-axis in a hydrogen atom? This is the question that we will also address on Friday. See you on Friday.